All right, here we go. So language one. This is the, by the way, the solutions to the three exercises I posed in the previous video. If you didn't watch to the end of the previous video, please skip ahead to the end and make sure that you, well, I guess you don't need to, but the idea was to find phrase structure grammars that generate these three languages. So if you forgot to watch the previous video, then pause it now and try to do that. Let's go through some solutions. Language one here is actually in the textbook, right? So yes, I stole it. We're going to go over it anyway, because even though it's an example in the book, even because like this particular language, 0 to the n, 1 to the n, for equal values of zeros and ones, this particular language is something we're going to look at in later sections as well, as a counterexample for something else. So a phrase structure grammar that generates this language. Well, in order to define these phrase structure grammars, it suffices to just list the productions, because the symbols in the vocabulary and the terminal symbols are kind of implied by what the productions are. So if you look through the productions, you can tell what the terminal symbols are going to be, and you can tell what all the symbols are because you'll just see them, right? They'll show up in the productions. And it's assumed S is our starting symbol as well. So I'm just going to list out the productions for these. So I need to start with S and do something. And the key to coming up with a phrase structure grammar for this language is to think of whenever you introduce a 0, you can also introduce a 1. And you can do it in such a way that it kind of grows from the middle, like an onion. An onion like grows from the center, right? And the layers grow outwards, and the layers expand as new layers grow in the middle. And it just it's kind of like come out and out and out, and it's going to produce more and more and more and more layers. But those layers are being generated at the center. So I love the onion analogy. So what I'm going to do is I'm going to say, let's replace this with a 0 on the left and a 1 on the right, and I'm going to keep my symbol S in the middle. And if I do that, then starting from S, I can get 0S1, and then I can replace my S with another 0S1. And that grows in the center, right? You see the new 0 and 1 that I introduce are in the middle. And then I can do it again, 0, 0, and then replace the 0 with a 0S1, and then it ends with a 1, 1. And now I have 3 zeros and 3 ones, and so on, right? I can do that forever. But I need some way to stop the process and result in a string which contains only terminal symbols, the zeros and the ones. And the way to do that is to replace your S with, well, it depends. Do we want to allow lambda in our language? Because if I have this production, S is replaced by lambda, it's possible to apply that production right away, and then lambda would be a word in the language, a valid word in the language. In this case, since I'm letting n be any natural number, which includes 0, in this case, lambda is something we want in the language. So what I want to do is, at any point along this process, replace the s with the lambda, and then the process ends. And lambda itself is going to be a possibility, as well as 0, 1 or 0, 0, 1, 1, and so on and so on. So in this case, I want lambda, but as you'll see in the next example, it's going to be a little bit different. So now, for language 2, I have to start my language with 2 zeros and then some number of 1s, but it has to be a positive integer value. So let's start with S, and the very first thing I think I want to do is put the 2 zeros in there. Now, should I do what I did before and sort of recurse on this S symbol? If I did that, then I would be able to do 0, 0, S and then replace the S with another 0, 0, S, and then I would get 4 zeros. That's not what I want. I don't want to be able to have like any even number of zeros. What I want here is to maybe introduce another non-terminal symbol. This is just for the sake of, for the sake of convenience, right? For the sake of the construction of the language, we're going to introduce a non-terminal symbol A. So now I have put my 2 zeros at the beginning, and now I have to take this A, and somehow, through some other productions, I have to turn that A into a string of 1s. Well, I can do something similar to what I did in the first example here, where there's this sort of recursive production which you can apply over and over and over again, any number of times, to give you a string of things. So what I'm going to do here is I'm going to have A. I'm going to say I can replace A by a 1A. The idea there is then 1A can be replaced by the A can be another 1A, and you'll see what I get if I start drawing my derivation tree is replace the A with a 1A, and I get that. And then replace that A with a 1A, and I get that. And then replace that A with a 1A, and I get that. And what I'm doing is I'm introducing a new 1 every time, but I always have that A at the end so that I can recurse and apply the production again to get another 1. But again, like the first example, I need some way to end this process, so A needs to stop. A needs to disappear somehow. So if I do what I did last time and say, let's replace A by lambda, then, at the end here, I could say 0, 0, 1, 1, 1, and then lambda, and that would end it. Okay, I didn't write the lambda because it wouldn't really appear, right? But the problem with lambda is that back in the beginning, when I had my 0, 0a, I could have replaced this with lambda immediately, and then I just would have ended with 0, 0. And that isn't actually a string in my language, because I'm supposed to have at least one in this language here. So one way I can fix that is, instead of ending by replacing an a with a lambda, end by replacing a with a 1. And then you would be adding, concatenating one more 1 on the end of your string, but it would make it such that whenever you drop out, you're going to have at least 1 at the end. That is one possible way to fix that so that it works with a positive integer number of 1s. Another way that you could do this is, instead of doing a 0, 0a, you could insert the 1 that you need right here and do a 0, 0, 1a, and then have a replaced by lambda to stop the process. And then that minimum 1 that you need would be already there. So that would be another alternative answer you could have come up with for this, to generate this language. All right, so let's move on to our third language. I saved this for last because it's the most complicated one. We want to make a phrase structure grammar that's going to produce this language, which is all bit strings with an even number of 0 bits. Now, basically what we need to do here is start constructing bit strings, but whenever I introduce 0, I have to introduce 2 zeros, actually. So I'm introducing the zeros 2 at a time, so that there will always be an even number. It could be none, or it could be 2 or 4 or 6 or 8 or whatever. But the tricky part is that you can have 1s occurring in between the zeros, and you can have any number of 1s, meaning possibly none, or possibly 100. So we need something like this recursive idea of a replaced by 1a. We need to insert that in between the zeros, both before, in between, and after, to make sure that we're allowing for the possibility of there being 1s scattered around the zeros in any possible way. So coming up with a set of productions that's going to allow any possible string that has an even number of zeros in it is actually pretty hard. And there's a lot of different ways of doing it. So I'm going to show you one possible way of doing it, but you may have come up with something which is equivalent, but looks a little bit different. So if you have questions, make sure to send me your ideas, and I can I can let you know if it works or not. So what I want to do is I'm going to use this A. I'm going to use this exact production, actually, and that's my A replaced by 1A is essentially going to represent. This is going to be some number of 1s. And then I'm going to use an A replaced by lambda to finish that off, so that it could be no ones at all. But the way I'm going to begin my production here with S is I'm going to say it could be that S is just a string of ones. So S, replace S by A, that's one possibility. The other possibility here is that you take your S and you introduce 2 zeros. And to introduce 2 zeros, I'm going to sort of draw down here. Basically, I'm imagining you might have some ones at the beginning. You're going to have a 0, and then you might have some ones in between, and then you're going to have another 0. And what I want to do is I want to basically create string segments of that format. Some number of ones followed by a 0, and then some number of ones followed by another 0. Just like that. And I don't want to put ones at the end, because what I'm going to do is loop this segment, like make it so that I can make another one. So I can have ones and then a 0, and then some ones and then a 0. And then I'm going to loop that, and it could be any number of ones each time, right? As long as it's ones, 0, ones, 0. Stop, right? So I want that. And so to make that, I'm going to have S replaced by A0, A0. Now remember, each A is going to be this production, which I guess I'll go ahead and write next. A can be replaced by 1A. That's going to make it so that each of these A's can sort of kick off its own recursion, which is going to produce like any number of ones, possibly no ones at all, which means that to finish each of those recursive strings there, recursive like processes, I'm going to replace A with lambda. And that's it. So what I have here is, oh shoot, I just realized I missed something. Let me go back here. Remember how I said I wanted to take one of these segments and then follow it potentially by another one? Well, the S is, this production is the thing that's going to do that, and I need to make that recursive. So I forgot to say that after the A0, A0, we're going to put another S. There we go. This production right here is really the crux of the whole thing. S replaced by A0, A0, S. This can loop around, and you can do this as many times as you want with more A0, A0 segments. And you end it by eventually replacing your last S with another A, and then every single one of the A's can turn into any number of ones. So I'm not going to draw the derivation tree for that, because it is going to branch out in lots and lots of different ways. But I will just sort of show you a small part of the derivation tree. We would start with something like this. That's a single production, and then we'll do another single production, A0, 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 S. And then we could apply productions replacing each one of these A's individually by more 1A's, and then a 1A, and then a 1A, and then a 1A, so to produce a long string of ones. So I'm going to say that I'm going to stop it here with just 4 zeros, and then say that by a sequence of productions, it's possible to produce something like 1, 0, and maybe I'll have no ones in the next slot, 0, and then maybe for the third A, I'll end up making 3 ones, 0, and then I'll make another single 1, and then a 0, and then the last S, actually, I should have had, I should have put another step in here where S gets replaced by A, so that production will apply right here, and give me another A, which let's have that one be 2 ones. So this is an example of like one particular string you could get from this, and you'll notice it has 1, 2, 3, 4 zeros. And it'll always be an even number. So that's it for this video. See you in the next one.